In the next lectures, we are going to study vector bundles. A priori, vector bundles are simpler than general manifolds because they have an intrinsic linear structure. Indeed, we already saw an example of a vector bundle, the tangent space of a manifold, an example that we will revisit in this lecture. In the next lectures, we will work with vector bundles. Okay? Essentially, a vector bundle is a family of vector spaces that is parameterized by the points of a manifold, and a family that varies differentiably. Okay? We already have seen an example, even if we didn't know at that point what a vector bundle is, and the example is just the tangent space of manifold. This tangent manifold was the disjoint union of the tangent spaces of M at every of its points, and these tangent spaces of M at X are all vector spaces whose dimension is equal to the dimension of the manifold M, right? In order to define vector bundles, first we are going to consider the local models for vector bundles. When we discuss the manifolds, the local model of a manifold is just an open subset of an Euclidean space Rn. In our case, a local model is going to be just of the form U times Rn, where U is an open subset of M, right? This is the trivial model of a vector bundle over U. Indeed, what we have over here is that if the first coordinate is equal to x, we have this space over here, which is the product of the singleton consisting of x and Rn, and obviously this is an n-dimensional vector space, which is going to be, by definition, the fiber of the point x. And obviously it is an n-dimensional fiber, right? So that's more or less the intuitive idea of what a vector bundle is, okay? A bunch of vector spaces that are disjoint and that vary differentiably with respect to x when x is varied in a manifold, plus the conditions that make this construction differentiable. Of course, for instance, we can consider CR vector bundles, and in order to do so, we have to consider extra conditions. Now let us define local charts for vector bundles. Okay, so first let us consider a continuous map from E to M. Continuous because a priori we can consider vector bundles that are just C0. Of course, if the vector bundle is CR, this map has to be CR. And a vector bundle chart on this PEM of domain U, where U is an open subset of M and dimension N, N is going to be the dimension of the fiber, okay? The fiber of a point X in M is just the preimage of X by P. And okay, so a vector bundle of domain U and dimension M, this dimension N is because here in the model we have that the fibers are vector spaces of dimension N, is a homeomorphism phi between the preimage of U by P and U times Rn, such that the diagram that is considered here is commutative. Okay, so here the map phi1 is the map that associates to a point xv that belongs to U times Rn, so that x is a point in U and b is a point in Rn. It associates the first component, it associates x. And so as a consequence, we have that the image by the commutativity of the diagram, we have that the image by phi of the fiber of the point X is just the singleton consisting of just X times Rn. So the fiber over the point X for this local model. Okay, so fibers are fibers of our vector bundle are going to be sent by the vector bundle chart to fibers of the model, right? And we can define this map over here phi sub x, because as we just said, phi is going to send the fiber of x to the set consisting of x times Rn. And so if we restrict to this preimage and we compose with the second coordinate, okay, we have just a map that is a bijection between the fiber of x and Rn, okay? And indeed, what happens is that the image of a point y here in p minus 1 of u is going to be as follows. The first coordinate is given by the commutativity of the diagram, okay? Because the first coordinate, it has to be just p of y. And the second component actually is given by this function phi. It's going to be phi of I is going to be phi sub pi applied to y. Okay, so we have this formula for phi. Of course, this actually defines, or it could be good to define, a structure of continuous vector bundle. But we want to consider CR vector bundles. So we have to introduce the definition of a CR vector bundle atlas over obviously a CR manifold M, right? And what we need in order to consider CR vector bundles are compatibility conditions exactly in an analogous way to the case of manifolds, in which when we want to define a CR manifold, we have to require CR compatibility conditions. So a CR vector bundle atlas is a family of vector bundle charts such that this bijection over here, right, is a CR diffeomorphism. But it's not just that. Since phi I and phi j are actually vector bundle charts, what we have is that the image of x times Rn is x times Rn. Indeed, the restriction of this change of coordinates to the set of the form the singleton consisting of x times Rn is a bijection of this set, okay? And we are going to require, okay, that this map over here is CR when we are defining a CR vector bundle atlas, but we are going to require also that when we fix a fiber, the map between Rn and itself is always a linear isomorphism, because we want a structure of vector space for the fibers of our vector bundle. So, in few words, this map over here has to be a CR diffeomorphism that is a linear isomorphism by restriction to every fiber over a point in the intersection of the domains of definition of the local charts. Okay, in particular, if we consider for phi j, the map phi jx, and we do the same for phi I, this composition over here, by our definition, has to be a linear isomorphism of Rn. So it is an element of the linear group, and that happens for every x. Indeed, in this way, we can define a map from the intersection of the domains of the local charts ui and uj that sends the point x to an element of the linear group, which is just the composition of the inverse of phi ix with phi jx. And obviously, since this is an isomorphism of Rn, it can be interpreted as an invertible matrix. Okay, so we can see this as a map from an open subset of our manifold to an Euclidean space, R to the power n squared. Okay, and if we are in a situation in which we are considering a CR vector bundle atlas, this map over here is CR. The maps Gij that we consider satisfy this condition over here. If we have a point x, which is in the intersection of three domains of definition of local charts of n, then we have three, in that point, we have to define that there are defined three isomorphisms of Rn. And what we are saying here is that the composition of Gij in X and Gjk in X, the composition of these two isomorphisms of Rn is Gik in X. That is very, very easy because you use that Gij in the point X is just the composition of these two linear isomorphisms. Jk in X is the composition of the inverse of phi jx with phi kx. And when you consider the composition of those two, the composition of this one with this one is just going to be the identity, and we are going to obtain the composition of phi ix inverse with phi kx, which is the definition of Gik. So we have that. Obviously, if we consider the transition function from a vector bundle chart to itself, what we get is the identity, because here we get the inverse of phi ix composed with phi ix. So we have these two equations, this one for every x in ui, and this other one for every x in the intersection of ui, uj, and uk, three domains of definitions of local charts of M. And so, because this family of maps satisfy these two conditions, we say that it is a cocycle of the vector bundle atlas. Indeed, these conditions define a cocycle. That's I don't want to get into more details, but it is called a cocycle exactly because these two conditions are satisfied. Okay, so we have yet to define a vector bundle, and so a vector bundle structure is going to be just a maximal vector bundle atlas. Okay, and we say that C, which is PEM and the maximal vector bundle atlas, is a vector bundle with base M, total space E, projection P, and fibers of dimension n if the vector bundle charts are homomorphisms to the product of open subsets of M and Rn, okay? We say that this space is a vector bundle, okay? It's essentially a maximal vector bundle. In general, this maximal vector bundle atlas is implicit, and we're not going to provide any possible vector bundle chart for a vector bundle, okay? It's going to be implicit, so in general, we are going to write just P, E, and M. We're going to write down when we consider a vector bundle, the total space, the base space, and the projection. And many times the vector bundle C is denoted by E, is denoted in the same way that it's total space, even if of course this is just an abuse of notation. Let us point out that a CR vector bundle is a CR manifold. Indeed, in our definition, we are requiring that the coordinate change between different vector bundle charts are CR diffeomorphisms. So in particular, a CR vector bundle is always a CR manifold. Given a vector bundle, the fiber P minus 1 of X, it is going to be denoted by psi of X or EX. We can use any of these two notations, right? So let us consider a vector bundle chart phi u, okay, such that X belongs to U. And we can actually use this vector bundle chart to give a structure of vector space to the fiber associated to the point X, okay? How is that? We have that phi is indeed a homeomorphism between the preimage of U by the projection map and U times Rn, right? And phi x is just, if X belongs to U, is a bijection between Ex and Rn. Now we can consider the unique structure of vector space in Ex such that this map over here is indeed an isomorphism of vector spaces, of course. And obviously, the question is whether this structure of vector space depends on the choice of the vector bundle chart, because if it depends on this choice, then we're not defining well a structure of vector space in the fibers, okay? What happens is that the definition does not depend on the choice of phi. If we have two different local charts, okay, and X belongs to the domain of definition of these charts, we are actually giving a structure of vector space to Ex such that the first map is an isomorphism. But that makes automatically the second map an isomorphism, okay? Because we know that the inverse of psi x composed with phi x by the definition of a vector bundle is indeed a linear isomorphism, is an element of the linear group. And so phi x is an isomorphism if and only if psi x is an isomorphism. And in this way, we have defined a unique structure of vector space on the fiber of every point that is independent on the choice of vector bundle charts. We can associate several constructions to vector bundles. For instance, consider a vector bundle psi BEM and a submanifold N of n. We can consider the restriction psi of n is the vector bundle whose base is n. The total space is the preimage by the projection P of n, and the projection is the restriction to the total space. The dimension of the fibers is the same for both cases. So how can we see this? If we have two local charts, two vector bundle local charts, okay, for our vector bundle, right, we can consider the transition function associated to these two vector bundle charts. Sorry, the transition function associated to phi and psi, right? And what happens is that G is going to be a function from the intersection of U and B to the linear group. Indeed, for instance, if we are considering the C-infinity situation, in which everything is infinity, this transition function is C-infinity. What is the transition function that is associated to, let's say, the restriction fiber bundle? Right. What happens is that since we are restricting to our base to n, we can consider here a local chart which could be the preimage of let's consider here a hat, the preimage of the intersection of U and N, and that is going to be mapped bijectively into the intersection of U and N times Rn, and we get something analogous for B, right? And what happens is that if we consider the transition function associated now to the vector bundle charts, sorry, phi hat and psi hat, what we get is that this transition function is just the restriction of G to the intersection of U, V, and N. And so obviously, for instance, if this map is C-infinity, then the restriction, if N, for instance, is a C-infinity submanifold, is also going to be C-infinity. And so in this way, we get a natural structure of vector bundle that, of course, is going to be of the same dimension because the fibers are still vector spaces of dimension n, right? So the restriction of, we can consider, in some sense, the restriction of a vector manifold, of a vector bundle, sorry, to the submanifold of the base. We're going to consider now the example of the tangent manifold of a given manifold. Okay, let's suppose that the manifold is C-infinity. So the tangent manifold is also a C-infinity manifold. And this tangent manifold is also a vector bundle. We already know that it is the disjoint union for every x in M of the tangent space of M at x. So it's a disjoint union of vector spaces, all of them of the same dimension. the dimension of these vector spaces, the common dimension is the dimension of M, right? If we consider now a local chart, that for a local chart for M, right, we can consider the differential of phi, which is just diffeomorphism between the tangent space of U, the union of the tangent spaces of M at every of the points in U, and the tangent space of B. But B is an open subset of Rn, so this tangent space is identified with B times Rn. And indeed, we have that if X is a point of view, the differential of phi at X is a linear map between the tangent space of M at X and Rn. Now we can use these definitions to provide a vector bundle chart for the tangent space of U. Okay, let's display how. We have here the tangent space of U, and we're going to send the tangent space of U bijectively to U times Rn. And if W is a tangent space, is a tangent vector to M at the point X, X is a point in U, we're going to send this to X, and here the image by the differential of phi at the point X by the image by that map of the vector of the tangent vector W. Okay, that is going to be indeed a vector bundle chart for the tangent vector bundle. And we have to consider now, if we have two different vector bundle charts, the transition function. So we consider now another local chart, psi from U prime to B prime, and consider G the transition function. Okay, transition function associated to the two vector bundle charts T phi and T psi, right? But this is going to be a map from the intersection of U and U prime to the linear group. And that sends X to the composition of the differential of psi at X with the inverse of the differential of phi at X. Okay? And the point is that if our manifold is C infinity, this map over here is C infinity, the transition functions are C infinity, and so in this way we have to find over the tangent space of M a structure of C infinity vector bundle. Let us consider now the zero section. Okay, we have a vector bundle P, E, M, and we can define a narrow map from M to E, which is the map that it is in the slide, is the map that sends a point X to the zero vector of EX, right? Just okay. Indeed, EX is a vector space, and we just choose the zero vector of this vector space, and it is easy to check out by using vector bundle charts that this map is indeed a differentiable inclusion. It's a differentiable, sorry, not only inclusion, it's a differentiable immersion from M to E. Indeed, in this way, we can consider M as a subset of the total space because we can identify M with its image by the zero section, okay? And in this way, we can consider M as a submanifold of the total space E. This lecture was the introduction to vector bundles. We gave their definition, we saw some elementary properties, examples. In the next lecture, we are going to continue studying the properties of vector bundles and in particular, the properties of fiber maps. Thank you for your attention.